Hey everybody, welcome back to the channel and our next YouTube video all about spectroscopy and the electromagnetic spectrum. So if you had me for Chem 1, you learned a lot about the electromagnetic spectrum. I think it's really cool to learn all about that and kind of how it relates to us in real life when we talk about radiation and all of that. If you didn't have me, that's okay. I'm sure you learned a lot about it as well. So I'm not going to go in super depth about the electromagnetic spectrum because you really don't need to know all too much. And I know that myself, Mrs. Bartholomew, and Dr. Clark go pretty in detail with the two equations that you need to know. So I'm not going to do any sample equations with those because they're pretty simple. But there is something that you do have to know that we didn't go into in Chem 1. So just stay tuned to watch all of that. Of course, the electromagnetic spectrum is just a range of radiation. So if you never heard the electromagnetic spectrum song on YouTube, make sure you go ahead and watch that because I promise you, you will never forget the electromagnetic spectrum. That song actually is opposite of this spectrum here. And sometimes you'll see it kind of flip-flops which one it starts off with. So this electromagnetic spectrum starts over at gamma radiation, and I have radio waves over on this side. So radio waves, microwaves, infrared radiation, visible light, ultraviolet, X-rays, gamma rays. Had to get one in there. So radio waves have your longest wavelength, and typically radio waves can be football fields long, one wavelength. So that means that the top of one wave to the top of the next wave can be over a football field long, and we call that one wavelength. So radio waves have very long wavelengths, and as I go across from right to left, in this case on this period or on this electromagnetic spectrum, the wavelength actually decreases. So you can start to see the wavelength is getting shorter and shorter until I get to the shortest wavelengths, which is gamma radiation. And gamma radiation, I believe, has wavelengths that are like the sizes of like viruses, very tiny. And we can also relate not just wavelength to those, but frequency. So the longer the wavelength, the shorter the frequency, which means that not as many waves pass through a point in a given period of time. So if you think about sitting on the dock on Lake Wallenpaupack, probably around this time of year, the waves are going to be very broad. So the waves have a very long wavelength, but not as many waves are going to hit your feet at a given point in time. So it's a very big wavelength, but therefore the frequency is very small. However, if you're sitting on the dock on the 4th of July, where there's like thousands of boats out on the lake, the waves are going to hit your feet very fast. And that's because the waves are much closer together. So the shorter the wavelength, the higher the frequency, the more waves are going to hit your feet in a given point of time. And that also relates to energy as well. So the longer the wavelength, actually the lower the frequency. Or I'm sorry, the lower the frequency, which means the lower the energy. So that worked out anyway. Therefore, radio waves have very low energy, which is why right now, when you're watching this, probably over Wi-Fi, that Wi-Fi is coming to your computer via radio waves and microwaves, kind of somewhere in the middle. And those waves aren't detrimental. Those waves aren't energetic enough in order to denature your proteins in your DNA or anything like that. Not very destructive type of radiation. However, X-rays and gamma rays, I mean, you might have had an X-ray done before, and you're not supposed to get so many of them done in a certain time of year. And that's because the X-rays are very energetic, and they're called ionizing radiation, actually. And they can ionize your DNA, therefore cause mutations, and your cells can start to multiply too fast, and therefore that can lead to cancer. So that's why you don't want to get too many X-rays in a year, and that's why your technician always leaves the room, actually. And that's also why they put a lead sheet over you, is because X-rays can't penetrate the lead sheet very easily. So long wavelength means a low frequency, which means a low energy. And those are radio waves, as opposed to gamma rays. these have a very short wavelength, a very high frequency, and a very high energy. And notice how the visible light region is very, very small in comparison to the rest of the electromagnetic spectrum. So the whole visible light spectrum fits in this really tiny section right here. But they kind of just blew this up so that way you could see the colors a little bit better. And you can always know the order in which it goes in, because literally it's infrared, which means below red. So, and then of course, red is the first color to come after that. Then red, orange, yellow, green, blue, indigo, violet, and then ultraviolet comes after that. A lot of times students are like, wait, what color comes first? You're not gonna have violet next to infrared and then red next to ultraviolet. So infrared, red, orange, yellow, green, blue, indigo, violet, and then ultraviolet. And of course, there are two equations we can use in order to quantitatively relate energy to frequency and frequency to wavelength and wavelength to energy. And you should be familiar with these. And the first equation is C equals lambda times nu, where C is the speed of light, and C is equal to 3 times 10 to the 8th meters per second. And this is the velocity that all electromagnetic radiation travels at. So it's not just visible light. Gamma rays travel at that speed, and radio waves travel at that speed. Everything does. I was looking at something before, I think, and they said it's kind of like the speed limit of the universe. Not many things, really nothing, can travel faster than light. So the speed of light is equal to the wavelength times the frequency. And of course, the wavelength is going to be in units of meters, because that's what C is in. So always make sure wavelength's in units of meters, and that your frequency is in units of hertz. And hertz is a 1/2. So it's like an inverse second unit. The second equation is E equals H times nu, where E is the energy of a particular type of radiation. H is Planck's constant, and Planck's constant is 6.626 times 10 to the negative 34th joules seconds. So it's joules times seconds. That's just a value that a guy named Max Planck actually recognized was the relationship between energy and frequency. So H is a constant. It is always going to be that value. And of course, the nu is the frequency again. So C equals wavelength times frequency, and energy is equal to Planck's constant times frequency. Now, both of these have that frequency variable in them. So what we are able to do is we can combine these two equations and actually get a new equation, which looks like this. It's just basically a new equation from both of these. And that equation is E equals HC divided by lambda. And I'm going to show you quickly how to derive that equation from those two. So I'm going to quickly show you how to derive that last equation from the first two. And you might be able to do this on your own, but I figured I would show you anyway. It's always a good idea to know how to algebraically derive new equations. It's not so fun when you're deriving new equations using calculus. I don't mind the algebra. So I have C equals lambda times nu, and we also have E equals H times nu. So what I'm going to do is just solve both of these equations for the frequency. So I'm going to divide both sides here by wavelength, and I have frequency is equal to C divided by lambda, and I'm going to divide both sides here by H. I don't know why I did it like that. Let me erase that. There we go. So those cancel. And here I have that frequency is equal to energy divided by Planck's constant. I'm going to set these equations equal to one another because both of these equal the frequency. So C over lambda equals energy over Planck's constant. However, normally you're going to see that this equation is set equal to energy. So let's isolate energy. And to do that, I'm going to multiply both sides by H. And therefore, I have a final equation that gives me E is equal to H times C over lambda. So it's up to you however you want to solve those problems. You can do problems like this that are asking for energy given the wavelength or vice versa. You can use both of the more simple equations up top, or you can use the more complex one. Ultimately, it doesn't matter because you should get the answer either way. And really, those are the only equations that you need to know for the electromagnetic spectrum. And like I said, I do a ton of practice with this in Chem 1. I'm sure your other teachers did a lot of practice with this as well. So that's the extent to which I'm going to go over them. Now, we talked a little bit about spectroscopy and spectrometry before, and we can use the electromagnetic spectrum as a means of performing spectroscopy as well. And of course, spectroscopy can help chemists determine the structure and the concentration of a mixture of species. And there's a few ways that we can do that. So what we're familiar with and what you learned in Chem 1 is when you hit an atom with a type of radiation, normally that it excites the electrons, right? We've talked about that. And you can identify elements based on the frequency of light that comes off of that. For example, if you have a copper solution and you were to make an aqueous solution of a copper solution and put it in a flame, or to heat it up, essentially, those electrons and the copper ions get excited, they jump up in energy level, they bounce back down, they emit green light. And that green light is a way of determining that that particular solution had copper in it. If you had me for Chem 1, I usually do the flame test in the front of the room. We shut all the lights off, you see all the different colors. It's really, really neat. But you can also study compounds with spectroscopy using the electromagnetic spectrum, and we're going to talk about that as well. So normally you have something that emits electromagnetic radiation anywhere on the spectrum, and you kind of bombard your sample with that, which is what it's showing right here. Your sample gives off some type of spectrum, and you can read that, and it helps us to determine what compounds are made out of. This is a huge thing that chemists do. If you take an organic chemistry class in college, I promise you, you will do lots and lots and lots of spectroscopy in order to identify what compound you might have produced as a result of a lab. Normally, you would do something called infrared spectroscopy, which I'll kind of show you in a little bit here. But again, let's talk about atoms quickly. So you can input some type of energy into an atom. In this case, we're going to input some energy into hydrogen atoms. Normally, this is done by heat, but sometimes you can do it through other forms of electromagnetic radiation as well. And you input some energy into some hydrogen atoms. So these are just atoms in a sample. And what happens is some of those hydrogen atoms get excited, and those electrons jump up in energy level. And when they jump up in energy level, we say that they're excited. And sometimes, and it looks kind of silly, but you can represent excited atoms by drawing these little squiggly lines around them. When you excite the electrons in an atom, they can't stay excited. So you input some energy, that energy goes toward the jumping of the electron to the excited state. And as soon as it does that, it has to come back down. What goes in must come out. And that's what's going to happen here as well. We have our excited hydrogen atoms, or the excited electrons in the hydrogen atoms. And they're going to release photons of light. And those photons of light, we can quantify, we can determine, okay, so what wavelength do those lights correspond, or does that light correspond to? Therefore, what frequency does that correspond to? And therefore, what energy transitions is occurring in this? And there's a whole type of chemistry that corresponds to this. Not my personal favorite type of chemistry, but you can in fact do lots and lots of calculations and calculus with this. So the excited atoms emit photons of light and then they return back down to their ground state. We've talked about exciting atoms before, and that's when your electrons get excited, jump up an energy level, they come back down, they emit light. You can use those equations in order to calculate how much energy those photons have, and therefore what part of the electromagnetic spectrum do they correspond to, which most of the time they're going to correspond to the visible light region, hence why they make different colors. But what about molecules? We only talked about atoms in Chem 1. Now we're going to focus a little bit on molecules. So what happens when I excite carbon dioxide? Well, there's actually a few different things that can happen. And before we go into that, we need to think of the bonds in molecules kind of as springs. They're not going to be fixed in place. Those bonds aren't just one length and that's it. They're constantly moving, right? Like a spring. So think of it that way. They can get bigger or smaller. They can go up and down. And I'm going to show you some videos that kind of represents this as well. So as we go through this, just think of them not as fixed, but rather they're very flexible. They're able to move. And if I take electromagnetic radiation of any type and bombard molecules with the radiation, there's three different things that can happen, three possible transitions. A molecule can have an electronic transition, it could have a vibrational transition, or it can have a rotational transition. And we're going to talk very briefly about these three types of transitions that can occur when electromagnetic radiation hits a molecule. The first type of transition is an electronic transition. And I remember in grad school, we did so much work with electronic transitions. You just need to know the very, very, very basic idea behind these. So let's consider, Rocco, get down. Get down. Rocco, get down. Let's consider the molecule ethane, and ethane looks like this, C2H6. So there it is. What types of bonds are in ethane? Yes, they are single bonds. Yes, they are covalent bonds, but are they sigma bonds or are they pi bonds? Hopefully you would say that they are sigma bonds. So they only have those s orbitals overlapping this way, or those sp3 orbitals overlapping that way. S orbitals for hydrogen, but sp3s for the carbons. So right here is a sigma bond between carbon and hydrogen. And I also have a sigma bond in between both carbons. Now that's crucial with these. So what happens is when I input a type of electromagnetic radiation, those electrons that are within those sigma bonds jump up into a higher energy level. And there's lots of chemistry behind those. Right now, they're in the highest occupied molecular orbital, which is also known as the HOMO. And they jump up into the lowest unoccupied molecular orbital, which we call the LUMO. And again, there is a lot of chemistry behind those. Basically, what that entails is that you have those sigma bonds getting excited, and they are now sigma star bonds. Again, just the very basics we're going to do with this, which is what the next part of this slide is. So an electron can jump from a lower energy state to a higher energy state, but instead of jumping up energy levels, they're jumping up in their molecular orbitals. So they're going from a lower energy molecular orbital to a higher energy molecular orbital. And this is always done either using ultraviolet radiation or visible light radiation. And that's because these are the highest in energy. It takes quite a bit of energy in order for electrons in bonds to jump up to a higher energy level. So basically, all you need to know for this is that it takes ultraviolet and visible light radiation in order for molecules to go through electronic transitions. And that's when their electrons go from a lower molecular orbital to a higher molecular orbital. Like I said, this was like grad school level stuff. I did so much work with these, and it's not too bad to learn, but it's quite tedious to understand and to really grasp the concept of it. But these are always done with ultraviolet and visible radiation. So that's an electronic transition. The second type is a vibrational transition. And vibrational transitions are interesting because, again, we have to consider that the bonds are flexible. The bonds are like springs. And that's the whole idea behind these different transitions. So I found this video that kind of shows you some of the ways that these bonds or these springs can kind of manipulate how they move. So I started it at one section, and we're not going to watch very much of it, but I just want to show you this because I like the animation behind it.
A water molecule has 3 atoms, 1 oxygen and 2 hydrogens, and 2 bonds. That gives it 3 modes of vibration: symmetric stretching, asymmetric stretching, and bending. More complicated molecules have even fancier vibrational modes, like rocking, wagging, and twisting. If you know how many atoms a molecule has,
so those are the different types of vibrational transitions that occur. So notice how we don't have electrons jumping around. We don't have any electrons going from one molecular orbital to another molecular orbital. What's happening is those bonds are moving because, again, they're on springs. So not literally, but figuratively, they're on springs. So we're moving and we're bending those bonds. Bonds don't have to be one length all of the time. Bond lengths that we have are basically on average what is going to be the distance from the nucleus of one atom to the nucleus of the other, or half of that distance rather. And we can get vibrational transitions to occur using infrared radiation. So notice how infrared radiation is less energetic than ultraviolet and visible light. We're not forcing electrons to jump here. All the infrared radiation is causing is for those bonds to kind of move back and forth. So I'll show this to you again. I like watching this. I think it's kind of neat. So we'll watch it one more time.
Oxygen and 2 hydrogens, and 2 bonds. That gives it 3 modes of vibration: symmetric stretching, asymmetric stretching, and
that
bending.
Happens when you put in infrared radiation.
Have even fancier vibrational modes, like rocking, wagging, and twisting. If you know how many...
I like that last animation. That's funny. So when you input infrared radiation onto molecules, it can cause vibrational transitions. And again, this occurs because chemical bonds are not fixed, but they're very flexible. And because they're flexible, your bond length and bond angles can be manipulated a little bit. And that's what the infrared radiation is doing. They're manipulating the bonds in a way that's causing them to stretch or to move in other directions. The last type of transition is a rotational transition, and you're probably very familiar with this if you use a microwave, because this is what happens in microwaves. So again, I'm going to show you a video. This video shows you what happens when a molecule is undergoing a rotational transition.
2. By definition, the waves have electrical and magnetic fields that change direction rapidly. For this oven, the direction of the fields change 2.45 billion times per second. Water will try to align with the radiation's electric field. The changing field rocks the water molecules back and forth rapidly, and molecular friction from this creates heat as the motion disrupts the hydrogen bonds between neighboring water molecules. Now,
so notice the difference between vibrational and rotational. Vibrational transitions are when the bonds are moving. Here, bonds aren't moving, they're in place. There's not enough energy being put in order for those bonds to move. In this case, the molecules are just rotating a little bit. So the way a microwave works is you input microwave radiation, which is actually less energy or less energetic than both infrared, visible, and ultraviolet. When that happens, so when you have a wave, right, a wave literally looks like this, which is what the video was showing. And as that wave is moving, the polar water molecules are attracted or repelled from the force, and they rotate back and forth like this. And essentially, that's what's heating up the water molecules. Like he said, it's causing friction, and that friction is allowing them to heat up your food. So notice how there's no change in the bond angles, there's no change in the bond lengths. All that's changing is the rotation of the molecules themselves. And this doesn't take a lot of energy. So that's why microwave radiation is what causes rotational transitions of matter. So the lowest in energy. And again, we could see this in our microwaves every day when you heat something up. And that's the whole idea behind these two sections in Unit 3. So this is all about spectroscopy and the electromagnetic spectrum. And this is also another section, I want to say 3.12 or 3.13, all on the photoelectric effect, which actually there's nothing really on the photoelectric effect, but it's just those equations at the beginning of this PowerPoint. So I hope that helped. I will have a supplemental worksheet for you to look at. There's probably not going to be too many questions on the types of transitions, only because this is a very, very, very basic idea that you need to understand. Electronic transitions occur from ultraviolet and visible light radiation. Vibrational transitions occur with infrared radiation, and rotational transitions occur with microwave radiation. If you have any questions, let me know. Otherwise, I will see you in the next video. Bye.